Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. If you own a business, you don't just want some profit. You want to get the maximum profit possible. And if you're manufacturing soda cans, you don't want to spend extra money on the aluminum. You want the minimum surface area for your target volume. This is the idea of optimization. It's where calculus transitions from an abstract math class into a multi-billion-dollar tool used by tech companies, engineers, and logistics experts every day. Today, we learn the systematic framework to solve these real-world puzzles. Now, before we jump in, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. The classic optimization problem usually contains two equations. The first one is what we call the objective equation. So the objective equation is usually the thing that you want to maximize or minimize, and this could be either profit, area, volume, or something else. And then the second equation is what we call the constraint equation. This is the limitation that you must work around, whether that be a fixed budget, a limited amount of material, or a target volume. And the goal here is to use the constraint to rewrite the objective equation so that only one variable remains. And once we do that, we can then find the critical points using the first derivative, and then find our max or min. So let's take a look at how we can do that through our first example. Here, a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He doesn't need any fencing along the river, so what are the dimensions of the field so that he can get the largest area possible? So let's go ahead and draw a simple diagram to illustrate this. So this blue line is that straight river, and what the farmer is going to do is he is going to set up fencing along this river, and the fenced off area is going to be a rectangle, so something that looks like this. Now he doesn't need any fencing along the river, so he only has three sides. So let's say that this side is x, which means this side is also x, and then the top side we can call that y. So now let's go ahead and write down our objective equation. The objective here is to get a rectangle with the largest area. So that tells us we're going to write down the equation of the area of this rectangle. So that's going to be A is equal to x times y. Now our constraint is going to be the limited amount of fencing that we have. And we have exactly 2,400 feet of fencing. So this means our 2x plus y must be equal to 2,400. So now we have set our two equations. And the next step is to use the constraint equation to rewrite the objective equation so that we only have one variable. And to do that, we can go ahead and isolate either x or y from our constraint equation. And here it would be easier to isolate y, so we're going to get y is equal to 2,400 minus 2x. So now we can go ahead and rewrite our objective equation area solely as a function of x. So we get a of x is equal to x times 2,400 minus 2x. And then we can distribute that, so that's 2,400x minus 2x squared. And now we can go ahead and take the first derivative. So a prime of x, this is equal to 2,400 minus 4x. And the idea here is we want to find our critical points. So we do that by setting a prime of x equal to 0. So we get 0 is equal to 2,400 minus 4x. And then solving for x, we get x is equal to 600. So one thing to note here is our domain. So here, x has to be greater than 0 because we can't have a negative side, and we also can't have a side that is equal to 0 because then we wouldn't have a rectangle. Now x must also be less than 1,200 because this rectangle has two sides that are x, and it also has a side that is y. So if x was equal to 1,200, then y would be equal to 0. And of course, x can't be greater than 1,200 because then y would end up being negative. So our domain here is x is greater than 0, but less than 1,200. So now that we found our critical point, make sure you just double check to make sure that that is in fact a maximum. And we can check that by doing our interval test. So from 0 to 600, we can check a test point. So let's say a prime of 1. That is going to be 2,400 minus 4, so that is greater than 0, which means our function was increasing in that interval. And then from 600 to 1,200, we can do another test point. So let's say a prime of 700. We can see that this is going to be less than 0, which means our function is going to be decreasing on that interval. So therefore, because the function is increasing before the critical point and then decreasing after, we know that x is equal to 600 must be a maximum. So now we can go ahead and finish off the question. We have one side, which is x, is 600 feet. We can go ahead and substitute into this equation here to find our y. So we get y is equal to 2,400 minus 2 times 600. So therefore, y is equal to 1,200 feet. This means the dimension is going to be 600 feet by 1,200 feet so that we get the maximum possible area. Now for our second example, we want to make a box with a sheet of cardboard. And we're going to do that by cutting out the 4 corners and then folding up the flaps on the side. So again, we're going to start by drawing a diagram. So we have a square cardboard, and the square cardboard has side length of 3 feet. So this side is 3, this side is 3. And then what we're going to do is we're going to go ahead and cut out 4 corners. So of course, in order for this to be a box, these corners must all be a square, so that we end up having the same height on all 4 sides. So what happens after we cut out these 4 corners is that we're going to go ahead and fold along this line, fold along this line, and this line. So you can see that this flap gets folded up, 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 and up. And this is what's going to create this open box. Now, same thing, we're going to start by writing down our objective equation. So here we can see that we want to maximize the box volume, which means our objective equation is going to be the volume equation. So we get V is equal to, so now because we don't know how big of a square to cut from the corner, that is going to be our variable x. So notice how they're all going to be x by x. So if we cut out a corner that is x by x, then whatever is left here, that is going to be 3 minus 2x. So that means the volume of the box is going to be the base times the height, and the base of the box is going to be 3 minus 2x by 3 minus 2x. So 3 minus 2x squared. And then the height of the box is just going to be x. So we have that times x. Now notice for this particular question, we don't actually have another constraint equation because our objective equation is already only in terms of one variable. So that means we can just write this as v of x is equal to x times 3 minus 2x squared. So same thing as earlier, we're going to go ahead and write down the domain of this equation. So here, x has to be greater than 0 because we had to cut out something in order to fold the sides up to make a box. But x has to be also less than 3 over 2. Because if x was 3 over 2, that would be half the side length, which means we're going to end up cutting away the entire cardboard and we would not have a base left. Next, we're going to go ahead and find our critical values. And to do that, we need to first take the derivative. So we get v prime of x is equal to, and I'm just going to be using the product rule here. So this will be 3 minus 2x squared plus x times 2 times 3 minus 2x times negative 2. And now I can go ahead and factor out a 3 minus 2x from both of these terms. And then I'm left with 3 minus 2x minus 4x. So this is 3 minus 2x times 3 minus 6x. And to find critical values, we're going to go ahead and set v prime of x equal to 0. And once we do that, we get two solutions. The first one is x is equal to 3 over 2. And then the other one is x is equal to 1/2. So now x is equal to 3 over 2 is not part of our domain, so then we can ignore that, which means we only have one critical value that is within our domain. And then the last thing that we need to check is to make sure that this is in fact a maximum. Now we can do that by doing our interval test. So if we draw our number line, and then we write down our critical value, which is 1/2. So we have two factors. The first one is 3 minus 2x. The second factor is 3 minus 6x. So picking a test point in that first interval, let's say a quarter, we would get this is positive, and this is also positive, which means that our v prime of x is going to be positive. And now picking a test point in the second interval, so let's say we pick 1, we would get this is positive, but now this factor is negative, which means v prime of x is negative. So that means our original function v was increasing here, and then it's decreasing here. So that confirms that our critical value is in fact a maximum. So therefore, to answer the question, we would have the corner squares that we cut out are going to be 1/2 feet by 1/2 feet. And now let's do a quick recap of what we covered in this video. In optimization problems, the first thing we need to do is to identify our target, because we need to figure out what it is that we're trying to optimize. And that is going to become our objective formula. And a lot of the times when we first start with the objective equation, we're going to have multiple variables in it. But in order for us to differentiate it, we have to get it in terms of just one variable. And we're going to use the constraint formula to help us with that. And once you've found your critical points, there are a couple of checks that you need to do. The first thing is to make sure that it's within your feasible domain. And the second thing that you need to check is that critical points only tell you that the tangent is 0 there, but it doesn't tell you if it's a max or min. So if you're looking for a maximum, make sure that the critical point is actually a maximum and not a minimum, and vice versa. And now it is your turn to give this a try. Can you find the solution to the problem on the screen here? Make sure to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.